Welcome to The Explainer. Today we are diving deep into two of the body's most critical electrolytes, sodium and potassium. Now, I know it might sound like basic chemistry, but trust me, the delicate balance between these two tiny ions governs just about everything, from our blood pressure and our nerve impulses to the very beat of our hearts. So let's get into it.
All right, here's our game plan. We're going to start by really understanding sodium's job outside our cells and the incredibly complex hormonal system that keeps it in check. Then we'll shift our focus and go inside the cell to see what potassium is all about, how the body keeps its levels in such a tight range, and finally, what happens when that crucial life-sustaining balance is lost. First up, sodium. You can think of it as the king of the fluid that surrounds all of our cells. We call this the extracellular fluid, or ECF for short. Sodium is the main positively charged ion, the main cation in this environment, and its whole job really is to manage all of that fluid.
So think of sodium as the master controller for this extracellular fluid. It dictates the ECF's volume, sure, but also its concentration of dissolved stuff, what we call its osmolarity. And this, in turn, decides how water moves between the outside and the inside of our cells. I mean, if you get this balance right, you have stable blood pressure, and your tissues get all the blood flow they need. But if you get it wrong, things start to go sideways fast.
Now, this right here, this is pretty incredible. The concentration of sodium outside the cell is hovering around 140 millimoles per liter, but inside, it's just 10. That is a massive 14-fold difference. And this steep gradient isn't some accident. The body spends a huge amount of energy to maintain it, because it's essentially a battery that powers a ton of other cellular processes. So how does the body manage all this sodium? Well, here's a fascinating little detail. Our gut just absorbs pretty much all the sodium we eat. It's basically an unregulated free-for-all, probably driven by a really primitive salt-craving center deep in our brain. What this means is the body has no control over intake. So instead, it relies completely on the kidneys to act as the ultimate gatekeepers, carefully kicking out any excess to maintain that perfect balance.
Okay, this next point is absolutely crucial. And it's a distinction that honestly trips up a lot of people. It's the difference between sodium mass and sodium concentration. Think of it like this. You're making a drink. The total mass is the total amount of powder you put in the glass. That part is controlled by a hormone called aldosterone. The concentration, on the other hand, is how strong that drink tastes, which depends on how much water you add, and that's controlled by a completely different hormone, ADH, which just manages water.
And this is a brilliant illustration of that very concept. In a condition like chronic heart failure, the body's response systems are in overdrive, and they cause it to hold on to a huge amount of both sodium and water. But here's the kicker. It often holds on to proportionally more water than sodium. So what's the result? The patient has a high total mass of sodium in their body, but because it's dissolved in so much extra water, the concentration actually looks low. It's diluted.
Okay, so we mentioned that aldosterone controls sodium mass, but how does that actually happen? Well, let's dive into the powerful, complex system that's pulling all the strings, the renin-angiotensin-aldosterone system, or as you'll hear it called, the RAAS.
This entire system kicks into gear the moment the body senses a drop in blood volume. It has these specialized pressure sensors, we call them mechanoreceptors, that are basically tiny biological pressure gauges, and they're located in really critical spots, in the heart, in the major arteries in the chest and neck, and most importantly, in the small arteries that lead right into the kidneys. Now, once that drop in volume is detected, the body doesn't just do one thing. No, it launches this coordinated four-part counterattack. First, the nervous system cranks up the fight or flight response. Second, that RAS cascade we just mentioned is activated. Third, ADH is released to lock down water. And fourth, the brain makes you feel thirsty, so you'll actually drink more. It's a real all-hands-on-deck emergency response. And the ultimate goal of this hormonal super team is really simple. Get blood volume and pressure back to normal, whatever it takes. The key players here, angiotensin II, aldosterone, and ADH, they all work together to force the kidneys to hold on to sodium and water, while at the same time squeezing the blood vessels to physically crank up the pressure. So let's zoom right in on the star player for sodium retention, aldosterone, and see exactly how it works inside these special kidney cells. First, aldosterone docks with its specific target, the mineralocorticoid receptor. This newly activated pair then travels into the cell's nucleus, where it acts as a transcription factor, which is just a fancy way of saying it finds a specific gene and flips the on switch. In this case, it ramps up the production of an enzyme called SGK1.
And here's where it gets really clever. That SKG1 enzyme goes and hunts down a protein called NED42 and inactivates it. Now, normally, NED42's only job is to destroy the sodium channels that sit on the cell's surface. So, by taking out the destroyer, aldosterone essentially saves the sodium channels from being broken down. The end result? More channels on the cell surface, all ready to pull more sodium out of the urine and back into the body.
But wait, aldosterone isn't done yet. At the exact same time, it revs up the sodium-potassium pump on the other side of the cell, the side that's facing the bloodstream. This powerful little pump does two things at once. It actively shoves all that reabsorbed sodium out into the blood while simultaneously pulling potassium into the cell. This is so important because it loads the cell up with potassium, perfectly setting it up to be secreted into the urine. It's a brilliant two-for-one mechanism.
You know, you might be wondering, cortisol, another steroid hormone, is floating around in much higher concentrations, and it can actually bind to that same mineralocorticoid receptor. So why doesn't it cause constant sodium retention? Well, the answer lies with this protective enzyme, 11-beta-HSD2. It sits right inside these kidney cells and basically acts like a bouncer at a club, degrading cortisol on sight and making sure that only aldosterone gets to activate the receptor. All right, with sodium's regulation pretty well covered, let's switch gears to our other key player, potassium. Now, if sodium is the king of the extracellular fluid, then potassium is, without a doubt, the king of the intracellular fluid.
If you remember one single thing about potassium, make it this. A staggering 98% of all the potassium in your entire body is locked away inside your cells. This means that the tiny 2% that's floating around in your blood is what we measure, and it's incredibly sensitive. Even a small leak from that massive intracellular reservoir can cause huge, dangerous changes in your blood levels.
And this slide really puts some numbers to that fact. The normal plasma concentration is kept in a very narrow, safe range, just 3.5 to 5.0. Now compare that to the concentration inside the cells, which is way up around 140. This enormous difference in positive charge across every single cell membrane in your body creates an electrical gradient. And that gradient is the fundamental power source for our nerves and muscles. And that electrical potential is precisely why potassium is so vital. The ability of our heart, our muscles, and our nerves to fire properly depends entirely on this gradient being just right. Even tiny shifts in the blood's potassium level can be a disaster. If it's too high, cells can become dangerously overexcitable, kind of like a frayed wire. If it's too low, they become sluggish and unresponsive, almost like a dead battery. So how on earth does the body manage this delicate balance? Well, it uses two main strategies. For all the moment-to-moment adjustments, it just shifts potassium in and out of that huge intracellular reservoir. But for long-term balance, it relies on the kidneys to control exactly how much is excreted from the body for good. So hormones provide that rapid, minute-to-minute control. After a meal, for instance, insulin's job is not just to move glucose into cells, but to move potassium right in there alongside it. During exercise, adrenaline does the same thing, pushing potassium into muscle cells. This is crucial because it prevents potassium from building up outside rapidly firing nerves and muscles, which would totally disrupt their function. And you'll want to remember this insulin effect. It becomes a key medical treatment we'll talk about a little later. There's also this direct trade-off with hydrogen ions, which are the things that set your body's acid level, or pH. When the blood gets too acidic, a state we call acidemia, the body desperately tries to fix the problem by hiding the excess acid, moving those hydrogen ions into cells. But to keep the electrical charge balanced, a positively charged potassium ion has to move out, which can dangerously raise the potassium in your blood. And the exact opposite happens when the blood isn't acidic enough. Okay, now for the long-term control, which is all about the kidneys. The kidneys are incredibly versatile. When your body's potassium levels are low, they can aggressively reabsorb pretty much all the potassium that gets filtered. But when potassium levels are high, the distal part of the nephron, under the influence of aldosterone, can secrete huge amounts of potassium into the urine to get rid of it. And this links potassium control right back to sodium. The single most important factor that determines how much potassium the kidneys secrete is how much sodium gets delivered to that final part of the nephron. When lots of sodium arrives, that aldosterone-driven sodium-potassium pump we talked about earlier goes into complete overdrive.
It works furiously to reabsorb all that sodium, and in exchange, it has to dump massive amounts of potassium into the urine. This is the exact reason why many diuretics, which work by blocking sodium reabsorption earlier in the kidney, have a major side effect of causing potassium loss. Now, let's explore the dangerous clinical consequences that happen when these finely tuned systems fail, starting with high potassium, a condition we call hyperkalemia. Hyperkalemia is defined as a potassium level above 5.5 millimoles per liter, and it really only happens for one of two fundamental reasons. Either potassium has shifted out of that massive intracellular pool and into the tiny extracellular space, like we saw can happen in acidosis, or the body is simply unable to get rid of potassium, which is a classic problem you see in kidney failure. This is a true medical emergency, and it's because of the devastating effect high potassium has on the heart's electrical system. As potassium levels climb, the ECG shows this predictable and frankly terrifying progression. It starts with tall, peaked T waves, which tells you the heart muscle is struggling to repolarize. Then the QRS complex widens, meaning the electrical signal is traveling way too slowly through the ventricles. Then the P wave disappears completely, and eventually the organized rhythm just degrades into this chaotic sine wave pattern, which quickly leads to cardiac arrest. The emergency treatment follows a very logical three-step process. Step 1. The most urgent thing is to protect the heart. We give IV calcium gluconate to stabilize the cardiac membrane right away. Step 2 is to temporarily hide the potassium by shifting it back into the cells using insulin and glucose. And finally, step 3 is to actually remove the excess potassium from the body for good, most definitively with dialysis. On the flip side, we have low potassium or hypokalemia, which is defined as a level below 3.5. This also causes really serious problems, but it does it by making tissues less excitable. This can show up as profound muscle weakness or even paralysis, dangerous heart arrhythmias, and even paralysis of the bowel, which we call an ileus. Now, treating low potassium requires extreme caution, and there are some golden rules you absolutely cannot break. First, you always give potassium in saline, never in a sugar solution like dextrose. Why? Because giving sugar would stimulate insulin, which would just drive the potassium you're infusing right back into the cells, making things worse. Second, you have to infuse it slowly to avoid shocking the heart. And third, and this is so critical, you must check and correct the patient's magnesium levels. The body simply cannot hold on to or properly use potassium without enough magnesium. You can think of it as the key that unlocks the door. So, to wrap everything up, let's apply what we've learned with one final thought experiment. We've established that aldosterone's job is to save sodium and to excrete potassium. So what electrolyte abnormalities would you predict in a patient whose body just can't produce aldosterone? What would happen if that master regulator was missing in action?